32-bit computers can only store signed integers up to 231 to 1. This is why we have run out of IP4 addresses and have entered the 64-bit era. However, the number 231 to 1, 2,147,483,647, is not as large as the number 1 trillion, which I seem to be able to display fine without my machine crashing. Can someone explain why this is?
I answer your question by asking you a different one. How do you count on your fingers to 6? You likely count up to the largest possible number with one hand, and then you move on to your second hand when you run out of fingers. Computers do the same thing. If they need to represent a value larger than a single register can hold, they will use multiple 32-bit blocks to work with the data.
You are correct that a 32-bit integer cannot hold a value greater than 2 to the power of 32 minus 1. However, the value of this 32-bit integer and how it appears on your screen are two completely different things. The printed string 1 trillion is not represented by a 32-bit integer in memory. To literally display the number 1 trillion requires 13 bytes of memory. Each individual byte can hold a value of up to 255. None of them can hold the entire numerical value, but interpreted individually as ASCII characters. For example, the character 0 is represented by decimal value 48, binary value 00110000. They can be strung together into a format that makes sense for you, a human. A related concept in programming is typecasting, which is how a computer will interpret a particular stream of zeros and ones. As in the above example, it can be interpreted as a numerical value, a character, or even something else entirely. While a 32-bit integer may not be able to hold a value of 1 trillion, a 32-bit floating point number will be able to, using an entirely different interpretation. As for how computers can work with and process large numbers internally, there exist 64-bit integers, which can accommodate values of up to 16 billion floating point values, as well as specialized libraries that can work with arbitrarily large numbers.
First and foremost, 32-bit computers can store numbers up to 232 to 1 in a single machine word. Machine word is the amount of data the CPU can process in a natural way, e.g. Operations on data of that size are implemented in hardware and are generally fastest to perform. 32-bit push use words consisting of 32 bits, thus they can store numbers from 0 to 232 to 1 in one word. Second, 1 trillion and 1 trillion are two different things. 1 trillion is an abstract concept of a number. 1 trillion is text. By pressing 1 once and then 0 12 times you're typing text. 1 inputs 1, 0 inputs 0. See? You're typing characters. Characters aren't numbers. Typewriters had no CPU or memory at all and they were handling such numbers pretty well, because it's just text. Proof that 1 trillion isn't a number, but text. It can mean 1 trillion, in decimal, 4096, in binary, or 281,474,976,710,656, in hexadecimal. It has even more meanings in different systems. Meaning of 1 trillion is a number and storing that number is a different story, we'll get back to it in a moment. To store the text, in programming it's called a string. 1 trillion you need 14 bytes, one for each character plus a terminating null byte that basically means the string ends here. That's 4 machine words. 3.5 would be enough, but as I said, operations on machine words are the fastest. Let's assume ASCII is used for text encoding, so in memory it will look like this, converting ASCII codes corresponding to 0 and 1 to binary, each word in a separate line. 4 characters fit in one word, the rest is moved to the next one. The rest is moved to next word until everything, including first null byte, fits. Now, back to storing numbers. It works just like with overflowing text, but they are fitted from right to left. It may sound complicated, so here's an example. For the sake of simplicity, let's assume that our imaginary computer uses decimal instead of binary. 1 byte can hold numbers, 0.9. One word consists of 2 bytes. Here's an empty 2-word memory. Let's store the number 4. Now let's add 9. Notice that both operands would fit in 1 byte, but not the result. But we have another one ready to use. Now let's store 99. Again, we have used second byte to store the number. Let's add 1. Whoops! That's called integer overflow and is a cause of many serious problems, sometimes very expensive ones. But if we expect that overflow will happen, we can do this. And now add 1. It becomes clearer if you remove byte separating spaces and new lines. We have predicted that overflow may happen and we may need additional memory. Handling numbers this way isn't as fast as with numbers that fit in single words, and it has to be implemented in software. Adding support for two 32-bit word numbers to a 32-bit CPU effectively makes it a 64-bit CPU. Now it can operate on 64-bit numbers natively, right? Everything I have described above applies to binary memory with 8-bit bytes and 4-byte words too. It works pretty much the same way. Converting such numbers to decimal system is tricky, though. But it works pretty well with hexadecimal.
You are also able to write this statement as false without your computer crashing. Smile at Scott's answer is spot on for certain calculation frameworks, but your question of writing a large number implies that it's just plain text, at least until it's interpreted. Edit. Now with less sarcasm, more useful information on different ways a number can be stored in memory. I'll be describing these with higher abstraction, i.e. in terms that a modern programmer may be writing code in before it's translated to machine code for execution. Data on a computer has to be restricted to a certain type, and a computer definition of such type describes what operations can be performed on this data and how, i.e. compare numbers, concatenate text, or XOR Boolean. You can't simply add text to a number, just like you can't multiply a number by text, so some of these values can be converted between types. Let's start with unsigned integers. In these value types, all bits are used to store information about digits. Yours is an example of a 32-bit unsigned integer where any value from 0 to 2 to the power of 32 minus 1 can be stored. And yes, depending on the language or architecture of the platform used, you could have 16-bit integers or 256-bit integers. What if you want to get negative? Intuitively, signed integers is the name of the game. Convention is to allocate all values from -2 and 1 to 2 and 1 minus 1. This way we avoid the confusion of having to deal with two ways to write +0 and -0. So a 32-bit signed integer would hold a value from -2,147,483,648 to 2,147,483,647. Neat, isn't it? Okay, we've covered integers, which are numbers without a decimal component. Expressing these is trickier. The non-integer part can sensibly only be somewhere between 0 and 1, so every extra bit used to describe it would increase its precision. Half, 1/4, 1/8. The problem is, you can't precisely express a simple decimal 0.1 as a sum of fractions that can only have powers of 2 in their denominator. Wouldn't it be much easier to store the number as an integer, but agree to put the radix, decimal, point instead? This is called fixed point numbers, where we store 1,234,100 but agree on a convention to read it as 1,234.100 instead. A relatively more common type used for calculations is floating point. The way it works is really neat. It uses 1 bit to store the sign value, then some to store exponent and significand. There are standards that define such allocations, but for a 32-bit float the maximum number you would be able to store is an overwhelming. This however comes at the cost of precision. JavaScript available in browsers uses 64-bit floats, and it still can't get things right. Just copy this into the address bar and press enter. Spoiler alert, the result is not going to be 0.3. There are more alternative types like Microsoft Net 4.5's big integer, which theoretically has no upper or lower bounds and has to be calculated in batches, but perhaps the more fascinating technologies are those that understand math, like Wolfram Mathematica Engine, which can precisely work with abstract values like infinity.
If you want to avoid error persistence